This is question 46 from the GATE 2021 EC paper, where we are given that the delay of the XOR gate is 3 nanoseconds and that the clock frequency is 500 megahertz for this sequential circuit. If the initial state is 111 and the output of the XOR gate is equal to 1, then what is the minimum number of triggering clock edges after which the flip-flop outputs become 100? Underneath the question, you will find the title of the NPTEL course or video relevant to this topic.
So in this question, we are given that the clock has a frequency of 500 megahertz, right? That is, the clock period is 2 nanoseconds, right? So the idea is clock has a period of 2 nanoseconds. This is clock, and this XOR gate has a propagation delay of 3 nanoseconds, right? So the XOR gate has a propagation delay of 3 nanoseconds. So it is 1.5 clock periods. So the fact that the XOR gate delay is greater than the clock period should give you that there is some indication of complexity in this problem. And in fact, the initial value of the flip-flops is 111, which means that so Q2 is 1, Q1 is not going anywhere, but it's 1 nonetheless, and Q0 is 1. So the inputs to this XOR gate is actually 1 1 at t equal to 0 minus. So let's assume that this clock edge is at t equal to 0. So something very close to the clock edge, but to its left is t equal to 0 minus, and immediately after the clock edge is t equal to 0 plus. So at t equal to 0 minus, we have that the inputs to the XOR are 1 1, but the output D2, right, the output of the XOR is feeding D2 is 1, when in fact you know that for this input combination the XOR gate should output a 0. So let's look at it in terms of the state sequence for this flip-flop, right? So the idea is, of course, whatever, so the way this sequential circuit works is whatever is on Q2 will go to Q1, and whatever is on Q1 will go to Q0, and what comes on Q2 is the is whatever is on D2. So this is what happens when you have a pause edge of the clock. When you have a pause edge, we assume that these are all positive edge triggered flip-flops, right? So let's look at the state sequence for this. So this is the initial state, t equal to 0 minus, that is the number. So what this column counts is the number of clock edges that have passed. So before the first clock edge, obviously 0 clock edges have passed. So D2 is 1 as given in the problem, and these are the next states. So of course these are the current states. So what will be the next state? Remember, Q2 plus is whatever is on D2, Q1 plus is, right, Q1 plus is whatever is on Q2, and Q0 plus is, that is the next state of Q0, is whatever is on Q1. And as things stand, what is on D2 is 1, so that is what will come as Q2 plus. What is on Q2 and Q0 are 1 1, and they will come on Q1 plus and Q0 plus respectively, right? So we have the first clock edge that happens, and these three have come here, right? Or to be more precise, the next state has arrived. But and also the time elapsed is in this column. So the idea is that since the inputs are 1 1 and they haven't changed, that is, the inputs to this XOR gate, which is Q2 and Q0, are 1 1, they haven't really changed. So from t equal to 0 to t equal to 3 nanosecond, the output will stay the initial value of 1, and at t equal to 3 nanoseconds, which is here, you will find that D2 flips. This happens at t equal to 3 nanoseconds because it has a propagation delay of 3 nanoseconds. Now as soon as d2 flip, you can see that the next state will that is the predicted next state is q2 plus, which was d2, is also flipping, right? So this will happen when and remember, we are given that the flip-flops really don't have much delay, where the propagation delay of all the flip-flops is assumed to be 0. So as soon as the clock hits, the flip-flop output will change. So now the clock, which has a period of 2 nanoseconds, hits first at 0, then at 0 nanoseconds, then at so at 0 plus it has become 1 clock, and it goes up again at 2 nanoseconds, the second clock edge, and at 4 nanoseconds it goes to the third clock edge. So the clock has hit with this as the next state, right? So the next state arrives here, 0 1 1, and you can see that with this as the next state, q2 and q1, right? So the idea is d2 is equal to q2 XOR q1 with a delay of 3 nanoseconds. Now as soon as at 4 nanoseconds q2 and q0 became 0 1, you will have to see that the value at 7 nanoseconds for d2, that is 4 plus 3 nanoseconds, this is where the effect of q2 and q1 becoming 0 and 1 respectively will come. That is, d2 will become at 7 nanoseconds equal to 1. This is d2, right? And of course till then d2 is 0, so the next state q2 plus, which will take on the value of d2, is this, and 0 1 comes over here, right? So on the next clock edge, which will be happen at 6 nanoseconds, clock edge number 4, the next state of 0 0 1 arrives. And for 0 0 1, you can see that q2 and q0 are still 0 1, and so therefore you are not going to see a change in the output of the d2 gate, output of the d2 at the input d2, that is the output of the XOR gate, for these values, for this current state. And so at time 7 nanoseconds, as we had shown before, d2 became 1, and as soon as d2 becomes 1, that goes as the next state, and this 0 0 comes here as the next state, and finally 1 0 0, which is the target of the problem, happens at t equal to 8 nanoseconds, which is the 5th clock edge. So the idea is 5 triggering clock edges had passed to get to 1 0 0, and so the correct answer is 5.